everyone, welcome back to Leetcode Simplified. I'm Alan and today we're going to walk through Leetcode 144, binary tree preorder traversal. Given the root of a binary tree, return an array of all node values in preorder sequence, root left right. We are going to solve this iteratively, not recursively, and simulate the core stack manually using a stack. This way, we avoid hitting recursion limits on large trees and fully understand what's going on under the hood. Here is my two-phase process. Phase 1. Pop the stack. Point curve to the pop node, then append its value to the result array. Phase 2. Append right child, then append left child onto the stack. Repeat this two-phase process until the stack is empty. Let's animate example 1 step by step. Given pointer root that points to node value 1 of a binary tree 1, node 2, 3. First thing first, append the root node value 1 onto the stack. Now begin the two-phase process. Phase 1. Pop the stack. Create pointer curve to point to the pop node 1. Then append value 1 to the result array. Phase 2. Append right child node value 2 to the stack, no left child. Repeat the process. Phase 1. Pop the stack, points curve to the pop node 2, then append value 2 to the result. Phase 2. Node value 2 has no right child. Append left child node value 3 to the stack. Repeat the process. Phase 1. Pop the stack, points curve to the pop node 3, then append value 3 to the result. Phase 2 won't happen because node 3 has no children. The stack is now empty. Terminate the process and return the result array that has all the node values in the preorder sequence. Move on to the second example. Given pointer root that points to the node value 1 of a binary tree 1, 2, 3, 4, 5, no, 8, no, 6, 7, and 9. First thing first, append the root node value 1 onto the stack. Begin the two-phase process. Phase 1. Pop the stack. Create pointer curve to point to the pop node 1 and append value 1 to the result. Phase 2. Append right child node value 3 and left child node value 2 onto the stack. Repeat the process. Phase 1. Pop the stack, point curve to the pop node 2 and append value 2 to the result array. Phase 2. Append right child node value 5 and left child node value 4 onto the stack. Repeat the process. Phase 1. Pop the stack, point curve to the pop node 4 and append value 4 to the result. Skip phase 2 because node value 4 has no children. Repeat the process. Phase 1. Pop the stack, point curve to the pop node 5 and append value 5 to the result. Phase 2. Append right child node value 7 and left child node value 6 onto the stack. Repeat the process. Phase 1. Pop the stack, point curve to the pop node 6 and append value 6 to the result. Skip phase 2 because node value 6 has no children. Repeat the process. Phase 1. Pop the stack, point curve to the pop node 7 and append value 7 to the result. Skip phase 2 because node value 7 has no children. Repeat the process. Phase 1. Pop the stack, point curve to the pop node 3, then append value 3 to the result. Phase 2. Append right child node value 8 to the stack, no left child. Repeat the process. Phase 1. Pop the stack, point curve to the pop node 8, then append value 8 to the result. Phase 2. Node value 8 has no right child. Append left child node value 9 to the stack. Repeat the process. Phase 1. Pop the stack, visit the pop node 9, then append value 9 to the result array. Skip phase 2 because node value 9 has no children. The stack is now empty. So terminate the process and return the result array that has all the node values in preorder traversal. Alright, if we clear on the process, let's jump right into Python. If no root, no tree, return empty array. First thing first, append the root onto the stack. Create empty array result to hold node values. Now begin the two-phase process and repeat as long as the stack is not empty. Phase 1 begins by popping the stack and point curve to the pub node, then append its value onto the result array. In phase 2, append the right child, then the left child, if any. This process continues until the stack is empty, then exit the process and return the array result that has all the node values in preorder sequence. Done. Let's mark the submit button. Boom, accepted. That's it. This solution runs in on time, where n is the number of nodes, and use OH space, where h is the height of the tree due to the stack. This method is clean, recursion free, and handles large trees without hitting stack limits. Understanding how to simulate recursion with a stack is a powerful skill in tree problems. If you're able to walk through this stack-based simulation step by step, you're building a foundation for tackling many more tree problems with confidence. If this helped, give it a like, leave a comment with any questions, and subscribe for more step-by-step Leetcode walkthroughs. I'm Alan and this is Leetcode Simplified. Thanks for watching. Hello everyone, welcome back to Leetcode Simplified. I'm Alan. Today we're going to walk through Leetcode 145, binary tree postorder traversal. Given the root of a binary tree, return an array of all node values in postorder sequence, left, right, root. We will solve this iteratively by simulating recursions using a stack. This helps avoid recursion limits on large trees and most importantly understand what's happening under the hood. Here is the trick. At first, traverse the whole tree in root, right, left order. Then at the end, we reverse the result to left, right, root with the postorder we want. Here is my two-phase process. Phase 1, pop the stack, point curve to the pub node, then append its value to the result array. Phase 2, if they exist, append left child first, then right child onto the stack. Repeat until the stack is empty. At the end, reverse the result array to get postorder. Let's animate example 1 step by step. Given pointer root that points to node value 1 of a binary tree, 1, node, 2, 3. First thing first, append the root node value 1 onto the stack. Now begin the two-phase process. Phase 1, pop the stack. Create pointer curve to point to the pub node 1, then append value 1 to the result array. Phase 2, node 1 has no left child. Append right child node value 2 onto the stack. Repeat the process. Phase 1, pop the stack, points curve to the pub node 2, then append value 2 to the result. Phase 2, append left child node value 3 onto the stack. No right child. Repeat the process. Phase 1, pop the stack, points curve to the pub node 3, then append value 3 to the result. Phase 2 won't happen because node value 3 has no children. The stack is empty. No node to pop. Return array result reversed. All node values will be in postorder. Let's move on to the second example. Given pointer root that points to node value 1 of binary tree, 1, 2, 3, 4, 5, no, 8, no, 6, 7, and 9. First thing first, append the root node value 1 onto the stack. Now begin the two-phase process. Phase 1, pop the stack, create pointer curve to point to the pop node 1 and append value 1 to the result. Phase 2. Append left child node value 2 and right child node value 3 onto the stack. Repeat the process. Phase 1. Pop the stack, point curve to the pop node 3 and append value 3 to the result. Phase 2. Node 3 has no left child. Append right child node value 8 onto the stack. Repeat the process. Phase 1. Pop the stack, point curve to the pop node 8 and append value 8 to the result. Phase 2. Append left child node value 9 onto the stack. No right child. Repeat the process. Phase 1. Pop the stack, point curve to the pop node 9 and append value 9 to the result. Skip phase 2 because node value 9 has no children. Repeat the process. Phase 1. Pop the stack, point curve to the pop node 2 and append value 2 to the result. Phase 2. Append left child node value 4 and right child node value 5 onto the stack. Repeat the process. Phase 1. Pop the stack, point curve to the pop node 5 and append value 5 to the result. Phase 2. Append left child node value 6 and right child node value 7 onto the stack. Repeat the process. Phase 1. Pop the stack, point curve to the pop node 7, then append value 7 to the result. Skip phase 2 because node value 7 has no children. Repeat the process. Phase 1. Pop the stack, point curve to the pop node 6, then append value 6 to the result. Skip phase 2 because node value 6 has no children. Repeat the process. Phase 1. Pop the stack, visit the pop node 4, then append value 4 to the result array. Skip phase 2 because node value 4 has no children. The stack is empty, so terminate the process. Right now, the result array contains values in root right left order. We will reverse the elements of the result from root right left to left right root post order, the order we want. Alright, to make this happen, let's jump right into Python. If no given root means no tree, no nodes, return empty array. Append the root node onto the stack and create empty arrays result to hold node values. Begin the two-phase process until the stack is empty. In phase 1, pop the stack, then point curve to the pop node and append its value to the result. In phase 2, if left child exists, append it onto the stack. If right child exists, append it onto the stack. If the stack is empty, terminate the process. At this time, elements in the result arrays are in root right left. Reverse them to left right root. Here's easy tip to remember. Make 2 tweaks to the preorder algorithm to get this postorder algorithm. Tweak 1. Append the left child first. This gives a root right left order. Tweak 2. Reverse root right left order to left right root post order, the order that we want. Oh, typo. Okay, we're supposed to append the root and left. Looks good. All the logic, all the coding, it all comes down to this. And now the moment we've been waiting for. Let's smart the submit button. Boom, accepted. That's it. This solution runs in ON time, where N is number of nodes, and use OH space where H is the height of the tree due to the stack. This method is clean, recursion free, and handle large trees without hitting stack limits. Understanding how to simulate recursion with a stack is a powerful skill in tree problems. If you're able to walk through this simulation step by step, you're building the foundation for tackling many more tree problems with confidence. If it helps, give it a like, leave a comment with any questions, and subscribe for more step-by-step Leetcode walkthroughs. I'm Alan and this is Leetcode Simplified. Thanks for watching. I'll see you in the next one. Hello everyone, welcome back to Leetcode Simplified. I'm Alan, and in today's video we're solving Leetcode 94 binary tree in order traversal. Given the root of a binary tree, return a list of all node values in order traversal. That is left subtree, root, right subtree. We're going to use recursion. The function will keep calling itself until it reaches the bottom of the tree, and then it will start returning results upwards. It means when the root is none, return an empty list. Otherwise, get the in-order result from the left child, then add the current node's value, then get the in-order result from the right child. Finally, combine and return the result. The coding is quite easy. Let me show you how. If the root is none, return an empty list. Otherwise, return the result from the left subtree, then concatenate with the root value. Then concatenate it with the results of the right subtree. And that's it. This one line elegantly captures the full in-order traversal logic. Let's take a closer look at the example below. Given the pointer root that points to the node value 1. Let's break it down step by step. We call the function with the given root node value 1, f1. The function will call itself with the left child of node value 1 plus node 1's value itself, plus the function will call itself with the right child of node value 1. Like above, f of 2 will call itself on the left child of node value 2, which is f4, plus the value of node value 2 itself, plus f of 5. F of 3 produce value 3 and f of 8. Node 4 doesn't have a left subtree and right subtree, so it's only return value 4. F of 5 return the left subtree f of 6 plus the value 5 itself plus f of 7, the right subtree. Likewise, f of 8 return f of 9, the value 8 itself. F of 6 and f of 7 return value 6 and value 7 because node value 6 and node value 7 do not have left or right subtree. Node value 9 has no left or right subtree, so f of 9 return value 9 only. Let's display all the values in one row. Now concatenate all the lists into one list. And that is all the node values in order traversal. This elegant one-line recursive solution is so clean compared to the iterative version. Get the entire traversal logic in one readable statement. Alright, time to smash the submit button. Moment of truth. Boom, accepted. Time complexity is O of n. We visit every node once. Space complexity is O of n in the worst case due to the core stack. And that's how you solve binary tree in order traversal recursively. We follow the classic left root right pattern, and Python list concatenate made it incredibly clean. Since the recursive approach is so elegant, and preorder and postorder traversals follow very similar logic, let me show you the full code to those as well. Move it out of the way. Create a function for preorder and another function for postorder. Change this to preorder. Change this to postorder. In preorder, we return the root value first, and in the postorder traversal, the root value will be returned last. And that's all I've got for today's video. All three binary tree traversals solved using the recursive approach in order, preorder, and postorder. It's just a few elegant lines of Python. If this helped you, Please like, comment, and subscribe to Leetcode Simplified for more clear, beginner-friendly tutorials. I'm Alan. Thanks so much for watching. Hello everyone, welcome back to Leetcode Simplified. I'm Alan, and today we're walking through Leetcode 100 same tree. Given two binary trees, check if they are the same. That means they have the same structure and corresponding nodes have the same value. We will use recursion approach, recursively traverse down each subtree at the same time and compare its pairs of nodes. There are three possible cases that can happen. Case 1. If both nodes are none, that means we reach the end of this branch and everything matched so far, return true. Case 2. If two corresponding nodes are not structurally identical, that means one node exists but the other doesn't, or both exist but their values are different, return false. Case 3. The two corresponding nodes match. We now recursively compare their left children and then recursively compare their right children. Return the result of both comparison. That's the full logic. Let's walk through three below examples to visually see how this works. Given binary tree with a root node value 1 and second binary tree also with root node value 1. We want to check if they are the same. Okay, so we call the function eSameTree with the root nodes of both trees. This node exists, and their values are the same. So continue, check their left children F2 and 2 and check their right children F3, 3. F2, 2, compare this node and this node, their values are the same, so continue, check their left children F none, none, and their right children also F none, none. So we are checking these two nodes. Because P and Q is none, then we return true. F none, none here also return true. Similarly, F3, 3, checking these two nodes, this node and this node. Their values are the same, so we continue checking their left children and their right children. Left children are none and none, and right children also none and none. Just like before, if both nodes are none, return true for that function. So F none, none, return true. At this stage, no more call, so we combine final answers true. Let's take a look at the next example. First, call eSameTree on the two root nodes 1 and 1. Both node 1 have the same value. Continue proceeding, checking their left and right children F2 none and F none 2. F2 none will check node 2 and none and return false. Because the AND operator, the whole process terminate and return false. Moving on to the last example, example 3. Like above, first call the function eSameTree on the two root nodes 1 and 1. Both nodes 1s are the same. F1, 1, continue calling their left children F2, 1 and their right children F1, 2. F2, 1 compare the value 2 and value 1 of the two nodes. Of course they're different, so F2, 1 return false. And since we have the logical operator AND in our return, we have early return false. Don't need to proceed any further. We just went through three examples. We walked down both trees at the same time, comparing each pair of nodes. If both nodes are none, good. If one is missing or their values don't match, return false right away. Otherwise, keep checking both left and right subtrees. Alright, time to submit. Boom, accepted. So that's how the recursive eSym3 function works. Clean and elegant solution that really show power of recursion for 3 problems. You found this helpful? Check out the other binary tree videos on the channel. I'm Alan and this is Leetcode Simplified. Thanks for watching. Hello everyone, welcome back to Leetcode Simplified. I'm Alan and today we're walking through Leetcode 101 Symmetric Tree. Given the root of a binary tree, determine if it is symmetric around its center. In other words, the left subtree and the right subtree mirrors each other. We'll solve this using a recursive approach, very similar to the technique we use for checking if 2 binary trees are the same. But here's the tweak. A symmetric function only takes 1 tree A parameters. So, to compare the left subtree and the right subtree to check if they mirror each other, we define a helper function isMirror that takes 2 parameters, left subtree and right subtree. We use isMirror function to recursively work down the left and the right subtrees at the same time in opposite directions. If one goes left, the other goes right, and vice versa. At each step, compare 2 corresponding nodes, one from the left subtree, one from the right subtree. Here are the 3 possible cases when comparing 2 nodes. Case 1. If both nodes are none, that means we reach the end of both branches at the same time and everything matched so far, so we return true. Case 2. If only one node is none, or both nodes exist but their values are different, the symmetry is broken, so we return false. Case 3. If both nodes exist and values match, continue comparing their children in the opposite direction. Compare the left child of the left node with the right child of the right node, and compare the right child of the left node with the left child of the right node. Then return their combined result. So what we're doing is mirroring our path down both sides of the tree, making sure each node on the left match its corresponding mirror node on the right. And finally, there's one special case to take care of. If the input tree is empty, it's symmetric by default. Otherwise, we want to check whether the left and right subtree of the root are mirror image of each other. That's exactly where we use our helper function. This call kicks off the recursive comparison between the left and the right sides of the tree, and from there, isMirror takes care of walking down both sides of the mirror directions, checking for symmetry all the way down. Let's take a look at a couple of examples to see this in action. Given this tree, check if this tree is symmetric around its center. That means the left subtree is a mirror image of the right subtree. First, call a symmetric function passing the root node 1. Asymmetric in turn call isMirror function with the left subtree and the right subtree of node 1. F2 to compare this node and this node of the 2 trees, and since they are the same, continue. Compare the left child of left tree with right child of right tree, and compare right child of left tree with left child of right tree. F3 tree compare this node and this node of the 2 trees. Their values are the same. So continue. Compare the left child of first tree with the right child of second tree, and the right child of the first tree with the left child of the second tree. All of these 4 nodes are none, so we have F, none, none, and F, none, none. If both nodes are none, that means we've reached the ends of both sub-tree at the same time, and everything's matched so far. Return true. Similarly, F44 continue checking the subtree of this node and this node on the opposite direction. This one go left, then this one go right, this one go right, and this one go left. And of course, they're all none. So return true. No more function calls at this time. So return the combined result true. Let's take a look at another case. Initially call asymmetric function passing the root node value 1. Asymmetric will call isMirror passing the left and the right nodes as parameters. F22 compare these two nodes, their values are the same. Continue, compare their subtrees in the opposite direction. Compare left of this tree with the right child of this tree, F non-3. And compare the right child of this two with the left child of this two, F3 none. F non-3 falls into case 2. One node doesn't exist, return false. And since we have the AND operator in our return, so we have early termination, we do not need to proceed any further and return false. So what's really happening here? We walk down both sides of the tree at the same time, comparing opposite positions. If both nodes are none, keep going. If only one node is none, or if their values don't match, stop right away and return false. If all pairs not pass this check, then the tree is symmetric. Alright, time to smart the submit button. Boom, accepted. So that's how the recursive asymmetric function works. A clean, elegant solution that shows how recursion can naturally handle these kinds of tree comparison. If you found this helpful, check out other binary tree videos on the channel. We cover traversal techniques, tree comparisons, and more. I'm Alan. Thanks for watching. Welcome back to Leetcode Simplified. I'm Alan, and today we're walking through Leetcode 104, maximum depth of binary tree. Given the root of a binary tree, return its maximum depth. In other words, calculate the number of nodes along the longest path from the root node down to the farthest leaf node. Let's walk through the elegant, short, recursive approach. First, if the node is none, return 0. No node, no depth. If the node does exist, return 1 for this node, adds to the depth. This might not be a leaf. We need to go deeper. Do that by recursively calling the same function on the left child and the same on the right child. Then take the larger of the two because we want the longest path and add it to the result. What we're doing is we walk down the left and right subtree of the current node. We hit a none, then return 0. We reach the bottom. If we hit a real node, return 1 plus the maximum depth from its left and right subtrees. Take a look at the example on the left with the given the root node value 3. First, call max depth passing the root node 3. F of 3 will return 1 plus max of F of 9 and F of 20, the left and the right subtree of node 3. F of 9 return 1 plus max of its left and right subtree, which is 0 because node 9 is a leaf, no left subtree or right subtree. F20 return 1 plus the max depth of its left subtree, F15, and depth of its right subtree, F7. F15 return 1 plus max depth of left and right, which are both 0. Similarly, F7 return 1 plus the max depth of its left and right, which are both 0. Let's write everything down all together. So 3 is the total of nodes along the longest path from the root down to the farthest leaf node. Alright, time to smash the submit button. Boom, accepted. So that's how the recursive max depth function works. Base case return 0 if the node is none. Recursive case return 1 plus max depth of left and right subtrees. Clean, efficient, and a favorite in coding interviews. If you found this helpful, check out the other binary tree videos on the channel. We cover traversal techniques, tree comparisons, and more. I'm Alan and this was Leetcode Simplified. Thanks for watching. Hello everyone, welcome back to Leetcode Simplified. I'm Alan. Today we're walking through Leetcode 111, minimum depth of binary tree. Given the root of a binary tree, return its minimum depth. In other words, calculate the number of nodes along the sorted path from the root down to the nearest leaf node. We will use recursive approach, which is elegant, short, and often asked in interviews. When recursively go down the tree from the given root node, we might encounter 4 cases. Case 1. If the node is none, return 0. No node, no depth. Case 2. If the node is a leaf, meaning it has no left child and no right child, then return 1, the node itself. Case 3. If the node only has one child, let's say it has no left child, then we need to return 1 to count itself plus the min depth of its right subtree. Same logic applies if it has no right child. Return 1 to count itself plus the min depth of its left subtree. Let's say node 3 don't have left child. Then at node 3 the function will return 1 plus the min depth of node 20, the right subtree. We don't take the min of left and right. If left is missing, it's not a valid path. Case 4. If the node has both left and right child, return 1 for the node itself plus the smaller min depth of the two subtrees. So what's happening overall? As we go down the tree, at each node, 4 cases can happen. If the node is none, return 0. If the node is a leaf, return 1. If the node has only one child, return 1 for the node itself, plus the min depth of its only subtree. If the node has both children, return 1 for the node itself, plus the shorter min depth of its two subtrees. Let's look at the example on the left. First, call the min depth function passing the given root node 3, f3. Let's move it out the way. f3 will return 1 and the smaller of its subtree min depth f9 and f20. f9, the min depth at node 9, return 1 for the node 9 itself because it's a leaf. f of 20, the depth at node 20, return 1 for itself plus the min depth of its left subtree f15 and its right subtree f7. Min depth at node 15, f15, return 1 for node 15 itself. Similarly, the min depth at node 7, f7, return 1 for node 7 itself. Let's bring everything down to one row. Final outcome is 2. As you can see, there are 2 nodes on the sorted path from the root down to the nearest leaf node. Alright, it's time to smash the submit button. Boom, accepted. That's the recursive solution to the minimum depth problem. It's handled missing children correctly. If you found this helpful, check out the other binary tree videos on the channel. We cover traversal techniques, tree comparisons, and more. Hello everyone, welcome back to Leetcode Simplified. I'm Alan and today we're walking through Leetcode 108, convert sorted array to binary search tree. This is a classic problem where recursion really shines, and we're going to keep our solution clean, efficient, and balanced. Let's dive in. Given a sorted array of integers in ascending order, convert it to a height-balanced binary search tree. Height-balanced means the depth of the left and right subtrees of every node differ by no more than 1. Our goal is to split the array in a way that keeps the tree balanced. Since the array is sorted, the middle element should be the root. That way, everything on the left becomes left subtree, and everything on the right becomes right subtree. Repeat this process recursively to build the entire tree. This divide and conquer strategy ensures balance because we're always picking the midpoint. Now let's look at the code in detail. First, if the passed-in array is empty, no more elements to process, we return none to indicate that this branch of the tree ends here and doesn't create a node. Otherwise, we're going to find the midpoint index and create a node with the middle value. Make it root of this subtree. Recursively build the left subtree using all values before the root. And recursively build the right subtree using all values after the root. Finally, we return the root node of this subtree, which connects the whole thing together. This allows the recursive calls to connect everything together and build the full binary search tree from the bottom up. Now let's take a look at the example on the left. Convert the sorted array -10, -3, 0, 5, 9 to height-balanced binary search tree. Let's go ahead and run the function passing on this array. Take the middle element and build a node with its value. Make it the root of the left subtree and the right subtree. For the left subtree, we call the function again, passing all the elements before 0. For the right subtree, do the same, call the function itself, passing all the elements after 0. Repeat the same process with the two new arrays, the left array and the right array. Get the middle element and create a node with its value. Make it the root of a tree. Same thing for array 5, 9. Get the middle element and create a node with its value. Make it a root node of a tree. On the left side, we have f of -10 and f of none. On the right side, we have f of 5 and f of none. -10 is the middle elements of a single element array. Create a node out of it and make it a root of a tree. 5 is the middle element in a single element array. Make a node out of its value and make it a root of a binary tree. Left of -10 is an empty array. Remember, if not nums, return none. So we return none. The right of -10 is also an empty array. F of empty arrays return none. Bubble up the result. Finally, we return the root. And there you go. We just convert a sorted array to a height-balanced binary search tree. Alright, time to smash the submit button. Boom! Accepted. And just like that, we build a perfect balanced binary search tree. Time complexities of this solution is O of n because we visit every node once. Space complexity is also O of n due to recursion stack and new tree nodes. This is about as efficient as it gets for tree construction from a sorted array. So that's the recursive solution to Leetcode 108, convert sorted array to binary search tree. It's clean, balanced, and leverage the sorted property perfectly. If you found this helpful, check out the other binary videos on the channel. We cover traversal, symmetry checks, and more. I'm Alan, and this was Leetcode Simplified. Thank you. Hello everyone. everyone, welcome back to Leetcode Simplified. I'm Alan and today we're walking through Leetcode 110, Balanced Binary Tree. Given the root of a binary tree, determine whether the tree is height balanced. That means for every node in the tree, the heights of its left and right subtrees differ by no more than 1. This single node tree is balanced. This single node tree is balanced. Its height is 1. Its height is also 1. The tree at root node 20 also balanced because the height of its left and right subtree differ by no more than 1. Its height is 2. This single node tree of course is balanced. Its height is 1. The tree at root 3 also balanced because the height of its left and right subtree differ by no more than 1. Its height is 3. How about this tree? A single node tree is always balanced. Height is 1 and 1. The tree at root node 3 also balanced because heights of its left and right subtree differ by no more than 1. Its height is 2. This single node tree is balanced. Its height is 1. This tree at root node 2 also balanced because heights of its left 2 and right 1 differ by no more than 1. Its height is 3. This single node tree is balanced. Its height is 1. The tree with root node 1 is not balanced because the height of its left right differ by 2. Here's the idea. Use a bottom-up recursive approach. Write a helper function that runs at every node and does two things. Returns -1 if the subtree rooted at that node is not balanced. Otherwise, it returns the height of that subtree as we see on the left. Let's translate this idea to Python. First, define the recursive helper function checkNode to be called at every node. This function will return -1 if the current tree is unbalanced or its actual height if balanced. If current node is none, means no tree, no height, return 0. It's our recursive base case as we can see all 0 on the left. Otherwise, if it's a real node, recursively check the left subtree, then recursively check the right subtree, and save their result into variables left, right. If either subtree is unbalanced, meaning it returns -1, or the difference in their heights is more than 1, then the current subtree is unbalanced and we return -1. Otherwise, return the height of the current subtree. So again, helper function checkNode return -1 if that subtree is unbalanced or its actual height is balanced. If the whole tree is balanced, result at check at the root won't be -1, so we return true. Let's take a look at the lab example step by step. Is the tree with root node value 3 balanced? It will call the check function to find its height or return -1 if the tree is unbalanced. F of 3 will return 1 plus max of its left f of 9 and right f of 20. F of 9 return 1 plus max of f of none and f of none, its left and right subtrees. If not node, return 0, so f none is 0, so the whole evaluation return 1. Similarly, on the right, f of 20 return 1 plus max of f of 15 and f of 7. Just like f9, the result is 1. f15 and f7 result also 1. The height difference between f15 and f7 is 0, so return the total evaluation would be 2. The height difference between the left and the right is no more than 1. Continue processing with the total evaluation. Let's copy everything down to one line. The result of f of 3 is 3, different than -1. So this evaluation return true. This tree is balanced. How about this tree? The only difference here is F7 return 1 plus max up 0 and 1. This whole evaluation return 3, and the height of the left and right subtree differed more than 1, so we return -1. So F3, instead of returning this, it returns -1. -1 is not different than -1. The whole evaluation return false. So this tree is not balanced. Alright, time to smash the submit button. Moment of truth. Boom, accepted. This solution is both elegant and efficient. Time complexity big O of n because we visit each node exactly once. Space complexity also O of h, where h is the height of the tree due to the recursion stack. And that's it. This is a clean recursive pattern that shows up in many binary tree problems. Check something at the children, bubble up a signal if something goes wrong, and return useful data if not. If you found this helpful, be sure to subscribe to the channel for more Leetcode walkthroughs like this one. I'm Alan and this was Leetcode Simplified. Thanks for watching. Hello everyone, welcome back to Leetcode Simplified. I'm Alan and today we're walking through Leetcode 112, path sum. Given the root of a binary tree and an integer target sum, determine if the tree has any root to leaf path such that sum of all node values along the path equals target sum. This is a fundamental binary tree problem that teaches us how to use recursion to check for a specific condition. In this case, whether a path from root to leaf adds up to a target sum. Here is our approach. We recursively explore its path from the root down to its leaf. At each step, subtract the current node's value from the target sum. At some point, when the node is none, return false. When the root is a leaf node, check its values against the remaining target sum. If not equal, return false. If equal, that means the sum of all node values along this path equals to the target sum. Return true. If we clear on the logic, let's make it happen in Python. If the root is none, that means the tree is empty, no path exists, return false. If the current node is a leaf, check if its value equals the remaining target sum. Otherwise, recursively check the left subtrees and right subtrees, subtracting the current node's value from target sum. If either subtree returns true, then there's a valid path that adds up to the target sum. Let's walk through the example on the left step by step. Is this tree with root 5 has a root to leaf path that sum up all values along the path equal 22. F5 22 will check with its left subtree passing on the reduced target sum, or its right subtree. F4 17 will check its left subtree or right subtree with the reduced target sum. F9 13 return false because if not root return false. F11 13 check its left and right subtree with the reduced target sum. F7 2 will check its left and right subtree with the reduced target sum. If not root return false. This one return false. So is this one. Since node 7 is a leaf, this function will check if 7 equals the remaining target sum 2, so return false. F22 is similar to F72, but node 2's values equal the remaining sum 2, so the evaluation return true. Bubble it up, false or true, return true. True or false, return true. Whatever on the left side right here, we don't care. True or whatever, return true. There is a path from root 5 to leaf 2, such that adding all values along the path equal 22. Alright, it's time to smash the submit button. Boom, accepted. This problem is a classic example of using recursion to explore all possible paths in a tree. It's also a great exercise in managing state, in this case reducing the target sum as we go deeper down the tree. Time complexity is O of n, where n is the number of nodes in the tree. In the worst case, we might have to visit every node once. Space complexity is O of h, where h is the height of the tree. This comes from recursion stack. In the worst case of a skewered tree, h could be n. In a balanced tree, it would be log n. If you found this helpful, be sure to subscribe to the channel for more Leetcode walkthrough like this. I'm Alan and this was Leetcode Simplified. Thanks for watching. See you in the next video.